Chapter 9, Solutions. Solutions are homogeneous mixtures of two or more substances. They form when there is sufficient attraction between the solute and solvent molecules. They have two components, the solvent, which is present in a much larger amount, and the solute present in a smaller amount. So our learning goal in this chapter, section 1, is to identify the solute and solvent in a solution and to figure out why something is going to dissolve in something else, which goes back to the saying like dissolves like. So if we look at our beaker of water, water's in greater amount than this salt, even though they're pouring a bunch of salt in. Water is the solvent, water and salt is the solute. It's just one in smaller amount. So solutes can be liquid, solids, or gases. They're spread evenly throughout. They mix with the solvents, so they have the same physical state. They cannot be separated by filtration, but can be separated by evaporation. They can end up giving color to the solution. So for an example here, if we add carpal 2 sulfate to water, notice it's very uniformly, after it dissolves, all of it dissolves, it's very uniformly blue. What a pretty color. So in table 9.1, it gives some examples of solutions. And so in the solution, we have solvents and solute. So solute plus solvent equals our solution. The one in greater amount is the solvent. Now, water is one of the most common solvents in nature. It's a polar molecule because of the polar O to H bonds. Remember that polar refers to acting partially charged. Let's look at this molecule, this representation here of a water molecule and the attraction. Notice how the partially charged negative oxygen of one molecule is attracted to the partially positive charged hydrogen of the other molecule. So, and then the beautiful thing about the water is it can do this with every single set of its atoms. It's not just one per molecule. It's all three, and they just are just showing just the one between, but it can be all three. The molecules form hydrogen bonds important in many biological compounds. So let's go back and review our hydrogen bonding. Hydrogen bonding exists between molecules only when hydrogen is attached to either oxygen, nitrogen, or fluorine atoms. Notice in the slide that the partially negative oxygen from one molecule is attracted to the partially hydrogen in the other molecule. And again, like I said, it's not just limited to one. We could draw more of these, and this hydrogen could be attracted to an oxygen of a water molecule, ditto for this hydrogen, and then it's just like, oh wow, it's just like very web-like. Hydrogen bonds are important in the properties of proteins, carbohydrates, and DNA. Now let's figure out why solutions might dissolve in each other. Well, they form when the solute and solvent have similar polarities, and it's the old like dissolves like. Now, let's see why our sodium chloride crystals would dissolve in water. Well, it's because they undergo hydration as the water molecules surround each ion and pull it into solution. Why do water molecules do that? Well, sodium, it's a metal, and remember, going back to ionic compounds, it's going to totally give up its electron to our chloride ion. So it's going to be totally positive, and yours totally negative. That is totally charged. And since water is polar, which means X charged, then, and like dissolves like, our sodium chloride will dissolve in water. And you think, why? Well, here's our sodium chloride, a representation of a whole bunch of our formula units of salt. And so our water molecule of oxygen being negative will go and attract to this positive of the sodium. And so will another water molecule. Pretty soon they'll just pull this all apart because of the attractive forces. Hence the term hydrated ions, and that's kind of what it's showing here. This is the process of dissolving. And why? Because like dissolves like, because there's an attraction there. Now, a polar molecule compound such as methanol is soluble in water because methanol has on one side of it this OH group. Now, you notice it also has this carbon to hydrogen, and that is not polar. So then you go, well, if part of the molecule is not polar and part of the molecule is polar, overall, what's going to be our net effect? Well, if the part that's nonpolar is not very big, then our OH still is able to perform and to go ahead and go in there and dissolve in water, in something polar. But as we change our methanols, our alcohols, and get longer chains of carbons, then it gets to a point where the carbon chain, the nonpolar part, is more of the boss, and its nonpolar activities make it where it's harder for the OH to do its job of dissolving in water. So polar solutes require polar solvents for a solution to form, i.e. like dissolves like. So first of all, on this learning check, let's identify the solute in each of the following solutions, like which one's a solute and which one's a solvent. Remember, solute's the one in smaller amount. Press pause and come back. Now, I'm hoping you can see that the solute here, the smaller amount, is the sugar. And here, the smaller amount is the methanol, or methyl alcohol. Here, the smaller amount is the 1.5 grams of sodium chloride. Here, the smaller amount, the solute, is the 200 milliliters of O2. Now let's go back and talk a little bit more about like dissolves like, and how the polarity of the solute and solvent must be similar, meaning charged, if they're going to dissolve in something else that's charged, or if they're going to dissolve in something that's not charged, then they need to be not charged in order to form this solution. So ionic salts, they act charged, and polar liquid, they act partially charged, dissolve better in polar liquids. They act partially charged than in nonpolar liquids. Hence, like dissolves like. So an example is, let's say that you have some Italian salad dressing, and if you know, you have to shake it up every time before you pour it on your salad. Otherwise, you're going to get the top layer out, and it's going to be all oil and not any of the other things in it. So you shake it up. Why? To mix it a little bit. Now notice we said mix, not dissolve, but we mix it a little bit, and then you pour it on your salad right after you've shaken it. You don't let it sit for very long. Why? Because the top part, the oil, which is nonpolar. Why is oil nonpolar? Because it's mostly carbons and hydrogens, and that total maximum electronegative difference is 0.4, which is not polar if you look back to our electronegative chart. And so the oil part is nonpolar. So it's not going to dissolve in the water or the vinegar portion of your salad dressing if you have your Italian salad dressing. Now then, in the salad dressing, the salt, though, because it is polar, sodium chloride, is going to dissolve in the water and vinegar section. Okay, now then, let's think about the other portion of your oil, of your vegetable oil in your Italian salad dressing. Well, the nonpolar liquids dissolve better in other nonpolar liquids than in polar liquids. So in salad dressing, the organic flavors are going to go in and dissolve in the salad oil. So a good salad dressing has both oil and vinegar, and maybe some water, so that both the salt dissolves, as do the flavors. Let's look at this learning check here. When solid lithium chloride is added to water, it dissolves because. Press pause and see if you can get this. All right, well, here's our metal. Metals are going to become positively charged, so they're going to be attracted to the negative portion of water, which is the oxygen. Our chloride ion, it's the negative charged portion, so it is going to be attracted to the positive charged portion of the water, which is the hydrogen atom. Which of the following solutes will dissolve in water and why? Press pause and come back. So let's look at our sodium sulfate. Well, we know that this is an ionic compound. The first one is a metal, so that's why it's an ionic compound, so it will dissolve in water. Why? Because like dissolves like, water is polar, and this is also acts very charged. Now gasoline, which is made up of mostly just carbons and hydrogens, if you do the electronegativity math on that, that is nonpolar, because the maximum you can get out of that is 0.4, and remember that classifies that as a nonpolar molecule. Well, because it's nonpolar, gasoline will not dissolve in water, and you already know that. You just didn't know why. Let's go down to D for a second. HCl. Now, hydrogen And chlorine, if you look at the electronegative chart there, hydrogen is 2.1 and our chlorine is 3.0. You do the math, 0.9, and that means it's going to act charge. It's polar. So because it acts charge, yes, it will dissolve in water. Okay, let's go to iodine. Now, if you do the electronegativity, even if you don't even have to look at the electronegativity map, but an I, whatever the value is for I, minus another value for I, the same value, is going to give you 0. So this is non-polar. And so it does not just dissolve in water. Why? Because it's non-polar, it doesn't act charged. Think back to your lab, your iodine clock reaction lab. You had a 2% tincture of iodine. And you may have wondered, if you looked at the SDS sheets, why it said there was some alcohol in it. Well, that's because this particular alcohol is ethyl alcohol, i.e. ethanol. And so it's got a little bit more of the non-polar portion of it, and it will help to dissolve the iodine. Now, part of your tincture of iodine is water, but part of it is your ethanol, your ethyl alcohol. And that is the portion that helps to dissolve our iodine. So if you were wondering, what the heck is this tincture of iodine and why is it the way it is? It's all about the saying like dissolves like.